Okay, so I forgot to mention in the last video that when we go through this algorithm, I always start by looking for holes. So I do this first because if there is a hole, there's going to be a factor that cancels. And for the rest of the question, I will use the resulting rest of the question. Okay. So let's try our first example here. I deleted part A, so we're starting with part B here. So the first thing I'm going to do is check for holes here. And so to do that, what I need to do is factor the numerator. The denominator is already factored. So I'm looking for two numbers that multiply to 2 and add up to 3. And I see that there are two of them, but neither one of them cancel with the factors in my denominator. So I don't have a hole, and I'll get started with the rest of it. So the next thing I'm going to check for are asymptotes. And I notice here in the denominator that I think there's a vertical asymptote, not that I think, I know that there is a vertical asymptote wherever the denominator equals 0. So that's what I'm checking for. You don't need to usually write that down. You can just go ahead and I think that you can look at this one by inspection instead of setting it equal to 0 and rearranging. By inspection, I can see here that the denominator will equal 0 when x is equal to 1. So that's my vertical asymptote. What I need to do though is evaluate the behavior near the vertical asymptote. So this is where I'm going to do my left and my right-sided limits. So I'm going to approach 1 from the negative side, and I'm taking the limit of f at x. Don't forget, I've seen this a couple of times where you guys write limit equals. You can't have the limit of nothing equals something. So it has to be the limit of something, and we're taking the limit of the function f at x. So I can write out the whole equation, or I can just write f at x. And here, there's nothing to stop me from taking the limit if I'm slightly to the left of 1. So in the numerator, it doesn't bother me at all to plug in the number 1, so I'll just go ahead and do that. In the denominator, I am going to have to consider the fact that I'm slightly to the left of to the negative side. And when I do that subtraction in the denominator, well, let's just clean up the numerator first. So I have taken the limit at this point. I subbed in the 1. When I do that subtraction in the numerator, I'm really close to 0, but I'm slightly to the negative side of it. And so I have this decimal that's really close to 0, but slightly negative. And then when I square that, I'm going to get a positive. So what I end up with here is 6 over almost 0, but slightly to the positive side. Remember, the squaring got rid of the negative for me. And I need to see this step here in order to figure out what kind of infinity. So when I'm dividing by 0, the answer is going to be infinity. Not 0, but almost 0. So I've got this tiny, tiny decimal in the denominator. So it's like I've got $6 on top, and I'm splitting it into piles of like 0.0000001. So I'm going to have a ton of piles, right? So that's my infinity. But now I need to know what this came down to simplify so that I can come up with the type of infinity. Is it positive or negative? So I needed to know that this numerator was positive and I was dividing by a positive. All right, so we know then on the left side of the vertical asymptote, I'm heading to positive infinity. So you might be thinking kind of in the back of your head, normally I would do this on the chalkboard, I've got my vertical asymptote at x equals 1, and on the left of that I'm heading to positive infinity. So what we figured out is that the graph goes like this on this side of the asymptote. I'm going to erase this in a second, but you might have it off to the side on a rough sheet of paper as you go through your work. We're kind of piecing together what the graph looks like. So now I want to know what's going on the right side. Is it also heading up to positive infinity, or is it heading down to negative infinity? So now I'm going to sub 1 into the equation, except when I get to the denominator, I need to think about the fact that I'm just slightly to the positive side of 1. So in the numerator, I'm going to get the same thing. I'm going to get 2 times 3 in those brackets. And then in the denominator, when I plug 1 slightly to the positive side, that inner bracket will be 0 slightly to the positive side. And so now I've got 6 over, and in the denominator, when I square 0, something slightly bigger than 0, I'm still going to be slightly bigger than 0. And so I've actually ended up with the same thing that I had over here. I've got a positive number divided by something slightly bigger than 0, and so that's going to give me an infinity. And I have a positive divided by a positive, so this one's also a positive infinity. So if I'm thinking about the graph, it tells me that I'm actually heading up on that side of the asymptote as well. So I'm keeping that in mind for later, and now I'm going to move on to the horizontal asymptote. So remember that we have those tricks from advanced functions for horizontal asymptote, investigating the degree of the numerator and the denominator, but I'm not going to use those tricks. I'm going to use calculus techniques, and then I'm going to check my work using the tricks. So to find the horizontal asymptote, I investigate the limit as x goes to positive infinity, the right side of the graph, and the limit as x goes to negative infinity. We'll do that afterwards. So when I take a look at the limit of this function, what I'm going to do, remember our trick for is I'm going to factor out the highest exponent on x. So I like this expanded version actually that I started with, and I'm actually going to expand the denominator as well to get me going. So I'm going back to the old numerator. And then when I expand out the denominator bracket, I'm going to get x squared minus x, so minus 2x, and then plus 1. And now we'll use that trick of factoring out the highest exponent on x. So I just divided each of these terms by x squared, and this was the result. And then I'll do the same thing in the denominator. I'm going to divide all of these terms by x squared since that was the highest exponent. And this is what we want to see when we're finding the limit as x goes to infinity. We want to have these x's in the denominators. So out front, our x squareds cancel. And so now I'm just taking the limit of this resulting expression. So in the numerator, the limit of 1 is 1. And then if I plug infinity into this expression, 3 divided by infinity is 0. And then 2 divided by infinity is 0. And we're talking about as I approach infinity, this gets closer and closer to 0. So the limiting value is 0. And then in the denominator, I get 1 minus 0 plus 0. And overall, then I have 1 divided by 1, which is just 1. So this tells me that I think that the horizontal asymptote is at y equals 1. Now we also need to consider the behavior as I go to negative infinity. So I want you to imagine how would this change if I were to put negative infinity in here. So if I'm going to erase this afterwards, but then I would put a negative sign here on my infinity and a negative sign here, but the work over here would stay the same. And then when I plug in negative infinity, I would actually get all the same answers. Remember, because it doesn't matter if it's positive or negative, 0, it's still just 0. So I'm actually going to get the exact same work. The only thing that changes is the positives to change to negatives. So instead of repeating that work, when there's only one simple change like that in mathematical proofs, there's a little shorthand trick. You can write similarly. So we love this word in mathematical proof. So similarly, if I were to plug in negative infinity instead of positive infinity, I will also get 1. Now, be careful. This trick gets overused, obviously, in mathematics because you're tempted to use it. You can only use it if everything would stay exactly the same except for one little change. If there were multiple changes, I would have to redo the work. So this is going to work out for us most of the time with a horizontal asymptote. So then we'll write our conclusion. Don't forget, we haven't written anything here about the equation of an asymptote, so you do have to tell me that the equation is y equals 1. It's a horizontal line, so it's going to be y equals a number. All right, so we've got our asymptotes. So I'm moving on to step 2 in our algorithm above. Step 2 was to look at the intercepts. And again, you don't have to do these steps in order. I could have done intercepts first. So for my x-intercept, I'll set y equal to 0. So above we had the factored version. I'm grabbing the factored version this time because I think it's going to help me out a little bit more. So setting 0 equals to the entire equation, I have one fraction equals 0, so I'm going to take that denominator and multiply it up on the other side. And that's going to give me 0 is just equal to the numerator. And I grabbed the factored version because this is nice and easy for me. I can just set each factor equal to 0. So I've got two x-intercepts. Now we're going to find the y-intercept. So this time I'm going to plug 0 in for all the x's in the equation. I'll use the original version this time, but it doesn't really matter. And so here I'm going to get 2 in the numerator, and in the denominator, -1 squared is +1, so 2 divided by +1 is just 2. So I have a y-intercept at a height of 2. So again, I'm piecing together, and you might be working on this off to the side, right? We're only done step 2 here, but we've got a lot of information. I know that there's a vertical asymptote. I know that there's a horizontal asymptote. I know that the behavior near the vertical asymptote is positive on both sides. I know that there's a y-intercept and 2 x-intercepts. So I'm kind of piecing together what this graph looks like. And this might make some of us uncomfortable here because we're going to have to cross over that horizontal asymptote in the middle of the graph to connect these points, but that is okay. So we'll get back to that in a minute. You just might be thinking about this off to the side. All right, the next step in our algorithm is to look at the max-mins and to find the maximums and minimums and the intervals of increase and decrease. This is kind of related. We're going to be looking at that first derivative. So I'm just going to copy down the equation here so I've got it. And here I don't want the factored version. It's easier for me to take the derivative if I have an expanded function. I'm going to leave the denominator though. You could expand it if you prefer. All right, so I'm going to take the derivative. This is a quotient rule, so I'm thinking about like the top of it being u and the denominator being v, and then the quotient rule tells me to do the derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. All right, so the derivative of the numerator times the old denominator minus, this time I'm going to leave the numerator alone, and I'm going to multiply by the derivative of the denominator. So here it's a chain rule. I'll bring the 2 out front, and now the bracket is raised to a power of 1. You can write that if you like. And then taking the derivative of the inner bracket, I would get a 1. And then in the denominator, squaring this bracket that's already squared, I'll have to multiply those exponents, and I get x minus 1 to the 4. All right, we need to figure out where this thing equals 0 and where it does not exist. So I am going to do some simplifying here. Since I want both 0 and does not exist, and I'm going to use this expression to test my test points in my chart, I don't want to set it to 0 and start rearranging right away. I'm going to leave it whole. And what I notice here is that there is a common factor of x minus 1. And so I'm going to pull that common factor out. So there's a factor in both terms of x minus 1. And then what I'm left with from the first term is 1 of each bracket. And then in the second term here, I'm just left with the 2 from over here times this bracket. And this is nice because now instead of dealing like, if I had expanded everything, I would have had a cubic expression. I've taken out one factor, so all I'm going to be left with is a quadratic, which is much easier for us to factor. Okay, so I'm going to expand out these two brackets here. I'm going to get 2x squared, and then I'm going to get negative 2x plus 3x, so that's plus x. And then I'm going to get negative 3. And then over here, I'm just distributing the -2 through the bracket. Okay, so collecting like terms then in the bracket, we actually eliminate our 2x squareds, so we're just left with a linear factor. Okay, so there's a couple of ways you could go here. At this point, I could start to look for where does my derivative equal 0 and where does it not exist. Or I do have a common factor, so I can cancel out this x minus 1 here, and then my denominator becomes cubed. So this is the form of the derivative that I'm going to use. Otherwise, I would have gotten a solution of x equals 1 and that it doesn't exist at x equals 1. And so overall, I would say it does not exist. It can't be a solution. All right, so there's our cleaned up version of the derivative. So we're going to investigate these two pieces. Remember that if I have a fraction and I want to know when the fraction equals 0, I really just have to investigate the numerator. And if I want to know where a fraction does not exist, then I really just need to investigate the denominator and where it equals 0. And so over here, when I rearrange and solve this, since it's linear, I can just isolate the x. So I'm going to get 7 divided by -5, which is -7/5. And you can be thinking about that as like -1.4, if that helps you kind of anchor it on the graph, but I'm going to use the fraction throughout my work. And then over here, when I rearrange this, I cube root both sides, I get 0, and then I add the 1 to the other side, and I get x equals 1. All right, so we've got our values to put in our chart. We've got two different values to set up our intervals. So we'll pick our test point, and then we want to investigate the sign of the derivative. And then I'm going to have a row here for f of x because I do want to know where it's increasing or decreasing. That is part of my algorithm, so I do want to see that as a statement. All right, so picking some number smaller than -7/5. So you could do -2. I'm going to do -10. I'm going to be plugging this into my derivative function. So I'm looking at this simplified version here. When I plug -10 into the numerator, I'm going to get +50 minus 7. So that's a positive numerator. And when I plug -10 into my denominator, I'm going to get -11. And when I cube a negative, I get a negative. So overall, this is a negative answer here, a positive divided by a negative. And so that tells me that my graph is decreasing at this point. So you could either like draw that, it's heading down in this interval here, or you can write the word decreasing. I'm going to have to write it in a sentence at some point. All right, I don't need a test point here. We came up with -7/5 here, which tells me that the derivative is equal to 0. And that tells me that my graph is going to be flat because my tangent line has a slope of 0. All right, picking some number between -7/5 and 1, I would pick 0. When I plug 0 into my equation here, I'm going to get 0 minus 7, so that's a negative numerator. And then when I plug 0 into the denominator, I'm going to get -1 cubed. And when I cube a negative, I get a negative. And so overall, this comes out as positive. So that tells me that I'm increasing on my graph. My slopes are positive, so I'm heading up on this section of the graph. And then for x equals 1, we came up with that value over here, which tells me that the derivative just does not exist. And then when I get this, I'm going to go back and take a look at my original equation and think about the domain of my original equation. So just scrolling way back up until we see our first equation. X equals 1 is a restriction on my original denominator, so the original function does not exist. We already knew that, right? This was our vertical asymptote. All right, and then picking some number bigger than 1. You could pick 2, you could pick 1,000, whatever you like. We're going to plug it into our derivative. I'm going to get negative 50 minus 7, so that's a negative number. And then plugging 10 into the denominator, I'm going to get 9 cubed, and that's a big positive number. So overall, I've got a negative divided by a positive, that's a negative. And so that tells me that this piece of the graph is decreasing or heading down. All right. So again, here you could be writing the words, like whatever makes more sense for you. And then I'll just kind of ask myself, do I need a sentence to actually write these words in them or not? And actually in this question here, they're not asking me to state the intervals of increase and decrease, so I'm not going to worry about that sentence. I do want to figure out, though, if there's any maximums or minimums. So I'm going to be looking for where does my derivative switch sign. And of course, the actual value would need to exist. The actual, like x equals 1 is not a critical point because the function does not exist. So I'm remembering that this is actually not. Right? We don't have a point here. We have a vertical asymptote. So this can't be a maximum, even though it's going from increasing to decreasing. It's just a vertical asymptote. So instead, the only point I need to take a look at is negative 7/5, and I am switching sign. I went from negative to positive, and so that tells me that there's a minimum there. Now I'm going to want to know the height of that because I'm going to want to plot this point. So I am going to go off to the side here and I'm plugging negative 7/5 into my original equation. So I can use the factored version or I can use the original. Oops, minus 1. And since I want this height so that I can actually draw the graph, I am going to change this to a decimal. This is 0.04. And again, you might want the x value as a decimal so that you can graph it. Negative 7/5 is the same as negative 1.4. So I've got my point there. We're going to add that to the graph as well. So I'm going to start to build my actual sketch now, remembering that I might need to calculate a few more xy pairs depending on if I have some gaps in my graph. So grab a sheet of grid paper. You're going to need some for this section of our course. What I have now, I have a few different points that I'm looking at. So I'm going to look through all my x values to try and decide where I should put my y-axis, right? Like, do I need to see more negative x's or positive x's? And it's pretty much in the middle. They're all pretty small x values that I have, positives and negatives. So I'll put my x-axis there. And then when I look at my y values, the smallest y value that I have, sorry, is negative 0.4. I made a little slip here. This is a negative number and a negative number. So that's actually below the x-axis. So I actually have, those are my only negative x values. Everything else is really, really high. So I'm going to put my axis like way down here at the bottom. All right. We'll add a scale to the graph. So I'm going to make sure that I can see up to a y value of 5 or higher when I do this. So I think I can go every 3. And then off to on the x-axis here, I want to make sure that I can see to -2 because I know that that's an x-intercept. I know that 1 is my vertical asymptote, and I'm going to want some x values on the right of that vertical asymptote. So I'm going to use a similar scale here. Okay, so we're going to start to add the information that we have. So I start with points when I add them. If I had a hole, I would add that to the graph, but I don't. I know that I have an x-intercept at -2 and -1. I know that I have a y-intercept at 2. I know that I have some vertical asymptotes that I could add in here. I'll add them in blue. So I've got a vertical and a horizontal. And you could have been building this graph from the beginning. It's just nice sometimes for scale to wait till the end so you don't have the axes in the wrong spot. All right, what else do we have here? We have the minimum point. So my minimum point is over at x is -1.4. So here-ish, almost halfway. And it's down at -0.04. So it is so close to the x-axis. It is like right here. I'm exaggerating a little bit. I'm probably putting it a little too low, but it is just dipping slightly below the x-axis here. And so remember that as I move to the left-hand side, I need to get closer to the horizontal asymptote. And then as I move towards x equals 1, I need to get closer to the vertical asymptote, and I'm increasing. Remember, we figured that out. Now I know that on this side, I'm getting closer to the vertical asymptote at positive infinity, but I need some points over here. Like I've kind of got like a no man's land. So I'm going to choose just some nice points in this section of the graph here. So I'm going to pick, oh, I did my scale poorly. I'm going to pick f at 3 is 5. So I'm going to plug this into the original equation and I get a height of 5. And then I am going to pick f at 4. And I can see it's not on my grid, but since I have a computer, I can just move. Don't you wish you had this? I can move this. So now I actually have 4s on my grid. So this is why you want to plan ahead and do a rough sketch before you go ahead and do your good sketch. When I do f at 4, I get 3 and 1/3. I didn't want to do f at 2 because it ends up being super high. It's at 12, and so then I'd have to stretch my y-axis, and it would be really hard to see this tiny, tiny decimal. Okay, so f at 3, I'm at 5. I'm adding these points to my grid. And here's my section of my graph over here. If from this point here, it is going to get closer and closer to the vertical asymptote, and then from this point here, it's going to get closer and closer to the horizontal asymptote. So it's actually coming down like this. So I don't get to see a whole lot of it, and this would be a smooth curve here coming up towards the vertical asymptote. All right, on this side here, this is like the thing that makes a lot of us uncomfortable. You are allowed to cross over a horizontal asymptote. So these actually join together, and this is okay because this is in the middle of the graph. And then I'm gonna dip and just connect to my minimum down here. And that's what this graph looks like. I'm gonna show you on Desmos. Don't forget that you can always check your work and zoom in. Oh, I forgot my Google Chrome crashed earlier. Okay, so I'll show you in the next video.